one thing Intel's been doing for the last couple of years has been transitioning to a product line called Intel oneAPI. Basically, this was kind of a shift that Intel was doing to represent Intel's new initiatives on GPU, in particular Intel GPU. And it was interesting, listen to Chris's talk. It's great having all these vendors here at the same time, because if you look at the tools, and conceptually what is different about the tools, there really isn't that much. I mean, over the years, they've really gotten quite similar, especially conceptually. I mean, visually, they look quite different. But I think having a presentation about exactly what is different about all the tools, it would be a much shorter presentation, because again, even with the open source tools, I mean, a lot of the concepts are the same, and a lot of the key concepts do get their start from academia, and they do make their way to the vendors. And things like Roofline, for example, that's been in the industry, in the academia for a long time. So today I'm going to start off giving a quick overview of Intel oneAPI and exactly what it is. If you're not familiar with it, I'll just touch upon that and just basically go into just a couple slides about what exactly it is and why you should care, and what you can do to take part. And then I'll go into Intel's tools, Intel vTune Profiler and Intel Advisor. These tools have been around for almost 20 years. vTune has been around at least 20 years. It really got its start as a CPU type of tool. Obviously, Intel has been focused on CPU, but we have been adding a lot of features for GPU. I'll touch upon all of the features, but later on, I'm going to focus mostly on GPU. We do have exercises that I've set up for CPU as well, but I'll let people pick and choose about what they want to try. If they want to try both, I'll be here. I'll be here all day today, most of tomorrow. If people want to set up a one-on-one session, I'm happy to do that. It's totally up to you. So I'll go into Intel vTune Profiler, Intel Advisor. I'll go into 3, 4, and 5 are really most of that is hands-on. So today, this morning, I'll cover 1 and 2, and then later on we'll cover what samples we have set up and what you can do to optimize for GPU and for CPU. Okay, what is Intel oneAPI? So obviously the industry has been going to not just CPU, but GPU, FPGA. Really, this has been going on for years. This is something that Intel has been doing. This is what the industry's been doing. So Intel is basically listening to our customers, and we want to be there to obviously make money. But again, a lot of the workloads. This is what they're doing. But unfortunately, a lot of the languages, they're not the same, and a lot of the programmers aren't the same. Whether you're running on a CPU or a GPU, it really is quite a different skill set. And obviously, you want to try to have as much breadth as you can, just to basically make yourself, so you can take part of this initiative. But again, it's hard because a lot of the languages are different. So what Intel's been trying to do is it's been trying to basically come up with the concept Intel oneAPI, where it's basically both an initiative and a product. The initiative is we have a spec for oneAPI, and basically all the vendors can basically hit that spec and basically come along with Intel oneAPI. So for example, if people want to use SYCL on NVIDIA or AMD, they should be able to take the same code that they wrote for one platform and move it to another platform. So if you did want to switch to a new hardware vendor, you have the ability. You wouldn't have to basically start from scratch. No one's saying you wouldn't have to do a little bit of work. I mean, obviously, if you've tuned for NVIDIA, it's thinking that would run the same on Intel. It's probably not going to happen. Hopefully, it will run. But even still, you'd probably still have to do a little bit of work as far as blocking. And there's a million things that you could potentially have to do. So that in a nutshell is Intel oneAPI. So again, the initiative. I'm going to touch upon data parallel C++, and this is kind of a marketing name because frankly, I found this very confusing because SYCL was the open source language, and that was a language that most people were familiar with. Data Parallel C++ is basically SYCL with extensions, but even that is kind of confusing. Really, it's easier to think of it. Data Parallel C++ is just the name for Intel's SYCL implementation. So we've been working with this language for several years. And again, conceptually, if you've programmed in C++, if you've programmed in CUDA, if you've programmed in any of that type of language, a lot of the concepts that you would see, OpenCL, for example, I mean, a lot of those concepts are very, very similar. The syntax is a little bit different, but again, you'd probably pick up that in a week. I mean, there really aren't that many. There's nothing really conceptually that's different. And again, the concept here is open source. I mean, basically an open standards implementation. You're not locked into any one vendor. And again, conceptually, you'd like to think your code would run multiple places. For example, if you're running C++, you would hope that C++ would run on an Intel machine or an AMD machine or a Microsoft machine or any machine. You shouldn't have to care. I'll just touch upon briefly Intel oneAPI libraries. If you've used libraries like MKL, for example, TBB, a lot of these libraries have been around for decades. They have hundreds of man years of optimization. We've basically taken that same set of libraries and we've moved them to oneAPI. So basically, we're trying to get a lot of those same algorithms, so they also run on GPU. So we haven't hit all of them yet, but that is the goal. So if you are using Python, for example, and you're using NumPy, Intel has a version of Python that basically does that is optimized for our platform. That we are trying to take advantage of GPU. So again, similar to what Chris was talking about, there's a lot of similarities there. Okay, I'll talk a little bit about the Intel product. So the Intel product basically is composed of several pieces. The first one is the language, which is SYCL. We also have all of Intel's compilers, C++, Fortran. Intel is one of the I think it's one of the best Fortran compilers around out there. But what we've done now, we have two versions of our compilers. One of them we call the classic version, which is the version that's been in Parallel Studio for a long time. The other version includes the ability to do OpenMP offload as part of Fortran in C++. So if you don't want to move to an offload specific language, you can basically just use OpenMP and hopefully that would be a much easier lift for you, especially if your code is in Fortran. Translating that to SYCL would be quite a lot of work. But I'm not trying to say that moving Fortran to OpenMP offload Fortran would be a trivial task. That's actually has a lot of complexities involved. OpenMP takes a lot of the complexities and they make it look like they go away, but they really don't. So we also have a tool called the compatibility tool that we've just recently open sourced. The open source version is called Cyclomatic. What Cyclomatic can do is it can take existing CUDA code and migrate it to SYCL. So hopefully it would get you 80% of the way there. We're trying to make that 90% of the way there. The parts that it can't migrate, we've tried to give you some hints about what you might need to do. If we haven't hit a particular API, for example, obviously that might be a little bit of work that you would need to do. But we're trying to make this code better all the time, and making that open source was just an easier way for that code to be adopted. And again, libraries, analysis, debug tools. It's funny how Chris says CUDA GDB. We have oneAPI GDB, so not a lot of uniqueness in naming here. Okay, so oneAPI basically is packaged in two different pieces. Actually, several different pieces. The first piece is called the base toolkit. The base toolkit basically includes everything I've listed up here, the compatibility tool, the compiler, Python, pieces for FPGA, all of our libraries. And then on the right-hand side is basically what I'm going to talk about for the rest of the presentation. Okay, please.
I have a question about the compatibility tool.
Yep.
So if I'm a developer on a library, an abstraction library like Raja, and I have different backends for CUDA and HIP, but I'm missing a single backend, would I be able to?
We have it.
So you'll be able to take the abstraction layers and map them into.
I have someone on my team who's working on that. Actually, he's working with Argonne on that. So we should talk afterwards. I can get you hooked up with some people who have a lot more experience than I have in that. But yeah, we're trying to work with the industry as much as we can. Please, any questions as I go along, I'm happy to answer. But I'm happy to answer at the end as well, and also as part of the hands-on. The hands-on, I figured would be a lot more informal. People are probably going to split off, and again, I'm here for most of the day. Okay, right-hand side is the analysis tools, which I don't think I've mentioned this, but I'm the manager of Intel's technical consulting group that focuses on analyzers, parallel runtimes, which is MPI, and all the TBB, for example, and also visual computing. So it's kind of a pretty broad set. I've only been manager for about a year. I was the lead for the analyzers for a long time. Then we have our APC toolkit. The HPC toolkit is basically meant to install on top of the base toolkit. So if you are doing things like MPI, if you want to use all the classic compilers, that's all part of the HPC toolkit. If you've used tools like Intel ITAC, which is basically lets you trace MPI programs, that's part of the HPC toolkit. Cluster Checker, Intel Inspector, that's also part of the HPC toolkit. Okay. Getting down to the nitty-gritty of compute analysis, we really have two profilers that basically can analyze GPU programs right now. The first one is Intel Advisor, and the second one is vTune Profiler. So I'm going to be doing a deep dive here in a minute, but I kind of wanted to go bit by bit about what features that they each have, and basically kind of give you some insights about maybe which one you should look at first, and conceptually what is each tool going to bring to the table. So the first one is Intel Advisor. Intel Advisor, again, got to start on CPU, but we've added 3 particular features to hit GPU. The first one is Offload Advisor. So Offload Advisor basically analyzes your program running on a CPU and tries to project how fast, which kernels could benefit from running on a particular GPU. So for example, if you want to say, how fast would this run on Intel's Gen 9 GPU? We could make that projection. We could tell you which kernels would benefit, what would the speed up be for each particular one, and which ones would not benefit, and why wouldn't it benefit? I mean, is it too much downloading, offloading is the offload time too big to make it worthwhile? So that is Offload Advisor. Basically, if you had a program and you weren't sure that it would benefit from running on a GPU, and you didn't want to spend the development time to actually implement everything, you could run a test with Offload Advisor and basically kind of get a ballpark estimate about what the speed up would be. It also has some pretty nice features as far as kind of do a what if analysis. What if the GPU I'm trying to analyze doesn't even exist yet, but I know it's going to have this much memory bandwidth. I know the caches are going to be this size. I know what PCIe is going to have. It lets you kind of tweak it and basically get a projection based upon that new configuration. So that's Offload Advisor. We can definitely experiment with that a little bit later. It has some nicer features where you can do everything from the command line, or you can use our GUI, but it generates an HTML page that you can share. It's kind of self-contained where you can actually see the kernels. Yeah, it's a feature that we've put a lot of time in recently. And then we have roofline analysis. Advisors have roofline analysis for a long time. We've basically ported that to our GPU. So again, conceptually, you can basically see how well your kernels are running on your GPU compared to what is the absolute best they could potentially be getting. So what this tool does is when you first start running, it fires off some benchmarks on your system, and it tries to get what is the maximum performance for all the caches, for all the compute, and basically tries to plot where your kernels are relative to the maximum possible. And then we have our flow graph analyzer, which is a piece that we've added recently, which basically adds a level of instrumentation to your SQL code and lets you generate flow graphs based upon what are the dependencies between the different pieces of your kernel. Pieces that you might not even know about. Pieces like that relate to memory, that relate to unified shared memory. All that would be basically displayed. It's kind of nice to see. I kind of view it as a learning tool because there could be a lot of dependencies that you're not aware of, and that is a way to optimize your code. If you're doing something and you have a dependency that's not necessary for offloading twice, for example, that the flow graph analyzer would show that. Okay, moving on to vTune. vTune Profiler is basically the flagship profiler of Intel's portfolio. Been around forever. We've added a couple features for GPU. One of them is offload performance tuning. So offload performance tuning basically, it's really the first step that I view that you would do when you were profiling for Intel GPU. Basically, it would show how your CPU and your GPU were interacting. So at what pieces are you running on your CPU? Where is your GPU busy? At what GPU utilization are you getting? Basically, it lets you visualize what is your program doing. And it does have a lot of details which you could get to at a deeper level. But offload would be the first step. The second step is GPU hotspots. And that is basically where you really get the deep dive about what's happening with your kernel. We have some pretty nice visualization as far as memory hierarchy diagrams where you can see each piece of your memory hierarchy, what's the bandwidth that you're seeing, and then some really detailed information about particular kernels and how many threads are running, for example. And that part is basically better shown as a demo, and I'm really happy to do that as part of the hands-on. Now to do a quick overview of vTune. So vTune, again, has been around forever. It really has a lot of features. We try to support basically every language that's out there. It has a lot of features which are specific to Intel hardware, specific to performance counters which exist. If you've used tools like Perf, for example, they use many of the same counters. But that's just one piece of what vTune can do. So vTune also has some technology. It's known as PIN, which basically lets us instrument your binary as it's running. So we can, at the simplest level, we can basically find out where your hotspots down to the instruction level. Basically, that's completely done in software. That doesn't rely on hardware at all. So if you're running on VM, things like software mode in vTune, it doesn't really care. But we also have some threading analysis tools. So what the threading tools can do is it can tell you not what functions are hot, what mutexes are hot. We can instrument all your threading APIs, for example, and basically show you how many times are you calling a given mutex, how much time are you waiting rather than doing useful work. So it really isn't one particular feature in V2, and it really is a set. And depending upon what you're trying to do, if you don't care about CPU, obviously you might not even hit those features. But we've really tried to make this tool accessible to as many people as we can. When V2 got its start, it really was a tool that gave a lot of benefits to computer architects. It really gave you minute details about how many times am I missing my L1 cache, how many times am I missing my L2 cache. But what we've tried to do recently is we've tried to make it a much more a metrics-driven tool, where a lot of things are built in by heuristics, where if you're exceeding any of our heuristics, a lot of things are flagged down, and we can basically take you down to the instruction and basically highlight what instruction and what particular line of code is problematic. And then, obviously, it's up to you. It's not going to fix the code for you. Basically, no tool can do that. Basically, it's going to give you some insights. For example, if you're memory bound, there's a lot of techniques that you could follow to get yourself unmemory bound, or get yourself so you're using memory a little bit better. Maybe your algorithm is just inherently memory bound, and there's not much you can do about it. But at least it's important to know. So, and then what V2 can do is it can let you try to make an optimization, and then do another run inside of V2, and then be able to compare the two runs side by side and see what's the delta between my first run and my second run. I mean, what changed? What lines are better? For example, how many times am I missing my cache now? I mean, did anything happen at all that was beneficial? So again, we really try to hit everything. All the languages that you're probably familiar with are supported. We're moving to a lot of the new interpreted languages like Go, for example, and Java, and obviously Python has been supported for a long time. But Fortran, C++, now SQL. But inherently, V2 works at the binary level. So if you didn't have sources, if some third-party vendor just plopped down some software, plopped down a binary into your cluster, and you wanted to see exactly what's going on, you could run VTune and basically get some insights into the program. I don't recommend it because if you don't have symbolic information, it's quite difficult. I mean, you might be able to see a lot of the same metrics, but you're not going to be able to do a heck of a lot about it. So, just on the right-hand side a little bit. So the first part here is basically what VTune presents to you when you're just getting started. I'm going to go into some of these features, so I won't talk specifically about it. But as you can see, there's quite a menu about what you can do. And then moving down, we have the source code level, talking about some of our GPU features. And then, again, similar to what Chris was showing, basically showing line by line about what exactly is happening in your program. You could hit the assembly button, again, if you're comfortable, and get right down to the assembly level. This bottom part here is the memory hierarchy diagram, basically trying to show you exactly what's happening at a really, really high level. What types of memory bandwidth are you seeing? How many times there's some information here on threads. There's some information on cache misses, for example. Again, a lot's going to depend upon what GPU you're running on, because each GPU has specific features that we can plug into, and they're not all the same. So once you bring up V2 knows exactly what hardware you're running on. So it basically configures itself to basically for the platform that you're running on. So your mileage may vary depending upon what hardware you're using. So for example, if you're using a multi-socket system, then a lot of the metrics V2 has are NUMA specific. So some of those metrics are key. I mean, if you ever run into NUMA issues, that can be really hard to debug. But V2 makes that really, really easy. There's a lot of metrics in there which are specific to that. How much time do I have? Okay. Some time. Okay, just going into some of the features. Algorithm optimization, those would be the features which are basically software based. But then moving over, we see some of the ones that I consider a little more interesting. Memory architecture and memory bottlenecks. Microarchitecture basically is going to give you probably the deepest level about what's going on with your microarchitecture. Things like, am I memory bound? But not just memory bound. It's going to go down as you cascade through its menu structure. It's going to give you details about exactly what is making your application memory bound. Is it your L1, L2? Is it something specific to NUMA where you're having to cross a remote DRAM access? All that's going to be presented But again, it does it kind of in a nice way where it's not going to just throw out this information. It's going to put it at a higher level, and it's going to let you cascade through the menus and basically get to the level that you're comfortable with. One feature that vTune is really, really great at is memory access. So what memory access does is it combines some of the hardware features of the platform with some of the software features that vTune has. So we can give you details about all your memory accesses, which would be specific to the hardware. So those are all the hardware counters that I've mentioned. But we can also use our software features, so we can track every memory allocation. So we can track how many times a specific data structure is having memory problems. I want to see memory bound because there's a million things that it could potentially have a problem with. So that's memory access. It's going to give you the most details about memory on your application. Moving over to the right, we have our parts that are specific to GPU. Again, we see our timeline here. Again, very similar to some of the stuff that Chris was showing earlier. Parallelism. Again, we have our timeline. We have you can't really quite see it here. It's kind of an eye chart, but the parts up top there aren't functions. They're mutexes. So how many times am I calling to give a mutex? How many times am I waiting? So a lot of these color codes that you can't quite make out here, they are specific. Some of it is where your CPU is running. Some of it is where your CPU is stalled. It just depends. Moving over here on the right, we have our platform and I/O diagram. So this is kind of a newer feature inside of vTune, where we've basically tried to show what does your system look like. In this case here, we have a 2-socket machine. You can see what disks and what PCIe cards are inserted here. Basically, it's going to give you a high-level description about what does your system look like, but it lets you kind of get down to a much lower level. One nice feature in vTune is taking a step back. vTune really is meant, if you're running it from getting the most details out of your application, it's going to collect a lot of information. So really, it's not meant to run for an hour. It's really meant to run your kernels for specific minutes. And again, we have an API that lets you target a specific region and basically only collect during this region. And that it gives you a little more wiggle room to basically run the kernel you care about for a longer period of time. But we also have a feature that lets you run all day. So if you had a workload and you basically wanted to see, is my system configured properly for this given workload, you could run this platform mode, and basically, rather than getting performance counters, which were actually tracing back to an actual PC and basically collecting a lot of information in stacks, the platform mode basically works by counting certain events. So rather than having to map every L1 cache miss, we basically can just count L1 cache misses. So that basically takes much, much less space. So again, that's a feature that is more from a system architecture point of view. If you're an application developer, that might not be as interesting. But again, it depends upon what you're trying to do. So the last feature here is multi-node support. vTune has several kind of umbrella products I like to think of them as. One of them is called Application Performance Snapshot, which basically is think of it as a script that you would run as part of vTune. So for example, you would run APS and then specify your MPI program, and it would get you kind of a vTune light kind of information. But that vTune light would also include a lot of the MPI metrics that you might be familiar with running ITAC. But since APS is much more lightweight, it can be supported on thousands and thousands of ranks. So APS is, my vision is APS is is where our MPI analysis is going from the oneAPI perspective. But ITAC is still there, and it's still used quite heavily by our customers. Okay, just an example. I wanted to kind of give some deep dive details about what features the vTune has. So vTune collects a lot of information just by the fact that it's running, but it doesn't present everything to you because it would just be very difficult to visualize it. So the first feature I wanted to draw out here is called grouping. So grouping basically is, I'm specifying here, give me the function in the call stack. So that's basically going to give me what functions are hot and what are the call stacks for that particular function. And then you have some visualization as far as how effective am I with my CPU utilization. I have some metrics for spin time. Again, in the bottom we have our timeline about where are we busy. But grouping, I did want to mention there's a lot of other groupings that we could potentially do. So if we wanted to basically see, do my threads have any affinity for a particular core? You could basically see what threads are running on each core. Or you could see which threads are running on a particular socket. So there must be 50 different groupings that you can do. Some of them are actually specific to OpenMP. We have a deep integration for OpenMP where you can get some metrics about how optimal is my OpenMP compared to what the ideal balance would be if everything was working perfectly. So that's something we spend a lot of time in. The bottom part here we call our filter bar. The filter bar basically is going to give you, ways of filtering for a particular process, thread, particular module. If you're only concerned about areas of the code that have bad utilization, you can specify that. There's all sorts of way to kind of filter out and only focus on what you're trying to do. If you looked at your timeline and you basically only wanted to, and you saw an anomaly, you basically saw, wow, I'm seeing a huge memory spike here. I wonder what's going on in the system during that particular time. You could select that part of the timeline and basically say, only show me the functions that were active during this part of the code. And then you could actually only focus on that part of the system. I'm probably going to have to start talking a little bit faster here. So there's a lot of features here. We have vTune works in all of our tools have a full command line mode or a GPU mode. If you wanted to basically run on your Mac, for example, and analyze your remote cluster, all that is fully supported. But frankly, one of the modes that I run into most commonly is I run on the command line on my cluster, and then I just copy the results back. It's just easier. The remote stuff is pretty slick, but it does require some setup. I'm kind of going to jump through here a little bit. I'm going to upload these slides as well. So consider this just basically some reference material. Okay, here's our memory access feature. You can see what memory objects and what latency they have. Again, latency is a pretty important metric. So basically you can see on average how much latency am I seeing? How many clock ticks is a particular reference having? So if you know what the latency of an L1 miss, for example, is, or an L2 or an L3, what are you seeing? Are you seeing a number that's like 5, or are you seeing a number that's like 300? So that's what this tool can do for you. Okay, microarchitecture. As you can see here, there's some pretty high-level metrics. If you hover over a particular metric, particularly the ones in red, it actually tells you what's happening here and why you should care. But it also lets you drill down into the lower levels. If you're back-end bound or you have bad speculation, if you're memory bound, all those are part of a higher level metric. And again, we have some nice visualization you can do. As you can see here on the left here, you can see some areas that have pink areas defined. Those areas are, pink is a highlight color inside of vTune. That's an area that we consider areas that you should be potentially concerned about. So on the left-hand side, we have L1. which is being flagged. We have L3 that's being flagged. And again, those aren't areas that we're saying are bad. They're just areas that we see that you're exceeding our heuristics. I'm going to jump over this a little bit, but as you can see, we've added some nice visualization here. This is input-output analysis. If you have an application that does a lot of I/O, this is something that you might find useful. This is a new feature that we've added called flame graph analysis. Again, this was just us responding to the industry. Flame graph was widely recommended by a lot of our customers, so we've added that feature. It is pretty slick. It's kind of, again, a lot of this is just reference material for you. This is again, a newer feature inside of eTune called performance snapshot analysis. So what this feature does is it runs a quick analysis of your application and basically tells you what you should do next. This is primarily a feature that would be used by a new user. So in this case here, we've done our performance snapshot. We kind of get a quick and dirty, high-level description of what's going on. What's our utilization? How does the microarchitecture look? Are we memory bound? How well are we vectorized? And depending upon what we see, it basically directs you about what you could do next for a deeper dive. Again, this is a kind of a quick picture of what of our application performance snapshot. How much of is my MPI imbalanced? And there's a lot of details here that I'm not going over. I only have a few minutes here, but I'll talk about Intel Advisor a little bit. Some of the main features, again, offload modeling that I mentioned, automated roofline analysis for both for CPU and for GPU. Intel Advisor really got its start as a vectorization advisor. Basically, what parts of your code are vectorized, what parts haven't been vectorized, and why wasn't the compiler able to vectorize? Especially if you're using the Intel compiler, there's a deep integration between Intel Advisor in the Intel compiler, where it really gives you some really key information. But then we have our thread prototyping tool. If you have a tool that hasn't been multi-threaded, and again, this feature was added over a decade ago, where there were a lot of codes that haven't been parallelized yet. This basically can analyze your code and basically show you, do a what-if analysis. What if this code was parallelized? What type of scaling would you see? And again, I mentioned flow graph analyzer. Okay, automatic vectorization. Again, it's often not enough. Actually, it's never enough. There's almost always work that you need to do. Kind of a quick snapshot about what the vectorization advisor looks like. Part of it is just the recommendations that advisor can give you. What performance issues are we seeing? How much CPU time are you spending? Is this particular loop scalar? Is it vectorized? Is it an outer loop that can't be vectorized? Again, why no vectorization? And then as you scale across these cells here, how has it been vectorized? How efficient is the vectorization? In this case here, we have an AVX2, but it's 67% efficient. So again, there's a lot of details here that I'm not showing. Here's a quick picture of what Offload Advisor can show you. As you can see, we've done a quick analysis. We can see how fast the code originally ran. We can see how much we're predicting the accelerated code would run. And then ultimately, what would be the ultimate bottleneck? In this case here, we're saying that we're ultimately going to be bounded by the LLC bandwidth. So again, if you were to move to a GPU that had higher LLC bandwidth, then that would be better. Sorry about that. And then in the bottom here, we have our what are the top offloaded kernels? What was the speed up? And then again, as you cascade through some of these menus, you get to a much deeper level about what's going on. And then what kernels weren't offloaded and why weren't they offloaded? Quick picture of what a roofline looks like. The diagonal lines that you see are the memory the memory caches, and the horizontal lines that you see are compute. And as you can see, we have one major hotspot that is color-coded in red. Your goal is to move your kernel up the y-axis. The x-axis is what's known as arithmetic intensity, which you can sometimes tweak a little bit, but a lot of that is going to be based upon what algorithm you're using and how efficient your compiler is. In general, your goal is to get as much flops as you can out of your system. Again, this is very, very similar, except all the roof lines are GPU specific. Okay, this next section is going to be purely what we're going to go over during the hands-on. I've put together several exercises. We can either do that, or I can show you, or you can just watch me do it. It's totally up to you. If people do want to get hands-on, I'm happy to assist them do that. We have the Intel Dev Cloud. If you haven't signed up, we can go through that exercise. I think we have a couple minutes here. Are there any questions? Or feel free to reach out to me later. I'm happy to answer them one-on-one. Please.
So, question about monitoring and analyzing large-scale executions with Intel's tools. So APS gives you a summary view. Is there anything that gives you a more detailed view? So like ITAC just shows communication.
It does.
Right? Is there anything that shows you any of the computation across the nodes?
APS does give you some of that computation. So it does give you information that's specific to memory. There is a lot of details in there, but I can see the point.
What I'm asking is, you collapse out the time dimension in APS, correct?
Right.
So there's nothing that shows you evolution other than ITAC, which only shows you kind of the communication level.
The best way to do that would be to do a deeper dive with vTune. So if you were using tools like Intel MPI, it does have some kind of cryptic syntax that basically says, I want you to analyze this set of ranks. So basically it would give you the ability to do a subset of your run. Okay. And then further than that, if you did instrument the code, you could basically get down to a kernel. So that would require a little bit more work. And the same thing with Advisor. Advisor, all of our tools, we try to fully support MPI, but not without some work. Yeah. Okay. Yep. And again, the platform profiler tool that I mentioned, that is the ultimate high level, but that's not going to get you the line information you're probably interested in. Okay, thank you very much.